The other miscellaneous methods in the ground improvement will be discussed. In that first one is micropiles. Micropiles, also known as pin piles, are small diameter, that is less than 300 mm diameter foundation elements, which are constructed by grouting the pre-drilled holes along with reinforcements. The bore holes are drilled with casings. Reinforcing bars are inserted and grouting is done by gradually removing the casing. They are non-displacement piles with a heavy reinforcement which can withstand axial and or lateral loads. The micropiles installation in different soils is possible and hence they are useful to support foundations for underpinning operations and for stabilization of slopes. To transfer the heavier loads, micropiles can be used in groups, and to achieve more capacity they can be pressure routed, which increases the lateral pressures and densifies surrounding soil. Now let us see the types of micropiles. The classification is based on the design application, and another classification is based on the method of grouting. So based on the design application, there are two types of case 1 and case 2 micropiles. In case 1 micropiles, the piles are directly loaded and the applied loads are resisted by the pile reinforcement and skin friction similar to conventional piles. Though they have used in groups, these micropiles are designed to act individually. In case 2 micropiles, the piles are provided in a network to make a reinforced soil and resist the applied loads. These piles are lightly reinforced because they are not individually loaded and the structural loads are applied to the entire reinforced soil mass. Now let us see the classification based on the method of grouting. So on the basis of pressure of grouting and placement method, the micropiles are classified as type A, B, C and D. Type A micropiles are prepared like the conventional piles by placing the grout material from bottom to top of the drill hole under gravity head. In type B micropiles, the grout material is injected first, followed by injection pressure through a pre-installed tube and by lifting the casing simultaneously. Clear cement grout is kept within the gap as the short-lived steel casing is withdrawn to improve the soil grout bonding. Injection pressure varies from 0.5 to 1 MPa, where stress is controlled to avoid damages to the surrounding ground. Type C micropiles are prepared by grouting the borehole under gravity head and then applying the pressure grouting through a sleeved pipe before hardening the first grout, approximately 15 to 25 minutes after primary grouting. Type D micropiles are like type C with a two-step process, but in this type, the primary grouting may be pressurized followed by additional grouting through sleeved pipe as many times as required to achieve the bond. Let's see the advantages of micropiles. The installation of micropiles is possible in different soil conditions, even in challenging site conditions, to support foundations of buildings, bridges, towers, small tunnels, highways, etc. The installation of micropiles is easy as simultaneous drilling and grouting is possible and they are economical also. The customization of micropiles allows the use of micropiles in rehabilitation of structures. Due to their versatile installation methods, they can also be used in underpinning and shoring works. As the equipment size is small, it is possible to install the micropiles in narrow areas. They have a high load carrying capacity and can resist axial, lateral and uplift forces. The installation of micropiles near existing structures is possible with restricted vibration and noise. Micropiles can be used for ground improvement and to improve the stability of steep slopes. The disadvantages of micropiles are the maximum load carried by vertical micropiles may be limited and may have low lateral stiffness. The usage of micropiles in conventional seismic retrofitting applications is not recommended due to their high slenderness ratio, where buckling causes loss of lateral support. There are no standard design procedures available to use the micropiles in slope stabilization. The applications of micropiles are ground strengthening and settlement reduction, structural stability and slope stabilization, earth retaining constructions and foundations, foundations for new structures, underpinning of existing structures, and seismic retrofitting. The next topic is diaphragm walls. Diaphragm walls are underground continuous walls of reinforced concrete, commonly used as retention systems and permanent foundation walls. Since they act as retaining walls, they are used to support dams, basements, deep excavations, and tunnels. The panels of these walls can be interlocked to make continuous barrier and facilitate water tightness. The thickness of diaphragm walls can range from 60 to 150 cm with a width of 2 to 3.5 meter, and the depth of diaphragm walls can extend up to 60 meter. The provision of temporary parallel beams called as guide walls adjacent to diaphragm wall, which is constructed prior to diaphragm wall construction, leads to proper alignment of diaphragm wall construction. Guide walls also avoid soil collapse and support the reinforcement steel cages. If the water table is high, the guide wall should be constructed above the ground level. The construction process of a diaphragm wall includes excavation of a trench in soil, placement of reinforcement, and placement of concrete into the trench with the trimming pipes. The applications of diaphragm walls are: they can be used in areas of dense infrastructure like underground car parks and railway stations, for underpasses and basements where a very rapid retention system is required, near existing structures where vibration and noise are to be minimal, in tunnels and deep basements where dewatering is not possible, in areas where the geology restricts a conventional retention system. The next topic is touch piles. Touch piles are constructed with intersecting concrete piles to form temporary or permanent retaining walls, commonly used for excavations in urban areas. The size and spacing of these reinforced piles can be adjusted to use them in different soil conditions or to tolerate the elevation changes. To form a continuous barrier, the space between the piles can be grouted or the piles can be overlapped. In secant pile walls, initially the primary piles are installed, and once they get sufficient strength, the secondary piles are constructed in between the primary piles with a pile overlap of around 8 cm. In a tangent pile wall, there is no pile overlap as the piles are constructed flush to each other. The advantages of touch piles are: the touch piles can be installed in different soil conditions, including cobbles or boulders. The touch pile walls are more flexible to align along a particular direction than the conventional concrete retaining walls. The touch pile wall has more wall stiffness when compared with the sheet pile walls. The noise due to construction is less. The disadvantages of touch pile walls are: it is difficult to achieve complete waterproofing of touch pile walls as they contain joints. The cost of a touch pile wall is higher than sheet pile walls. Now let us see the construction procedure of touch piles. Construction of secant pile wall of type hard to soft or hard to firm. This type of secant pile wall is generally used for temporary water retention, where the wall is made of interlocking board piles. The primary piles are made of either soft material such as cement bentonite mix or firm material such as concrete, whereas the secondary piles are made of reinforced concrete. These walls are useful in permanent works by providing a reinforced concrete lining. Next one is construction of secant wall of type hard to hard. The secant pile wall is generally used for permanent works, and it is an alternative to diaphragm wall. In this type, both primary and secondary piles are constructed with reinforced concrete, and hence it is not required to provide a lining wall. Next topic is soil liners. As the solid waste contains different types of waste, the leachate generated within the waste may contain different types of harmful chemicals. This leachate if it is not properly regulated, may migrate through the landfill liner and contaminate the groundwater. Hence, the design of the liner system is a crucial task in solid waste management, which requires knowledge of different types of waste, chemical composition of leachate, types of liner systems, compatibility of liner system, etc. The compatibility study of a particular liner system needs to be carried out for each of the harmful chemical constituent present in the leachate, for which knowledge of different contaminant transport processes is essential. The cost of compacted soil liners varies with the thickness of the liner and transportation costs from sources of clayey soils. The required thickness of clay liner varies from 50 to 200 centimeter in different countries. Types of soil liners. The most commonly used liner systems are geosynthetic clay liners and compacted clay liners. These liners are ideal to reduce or retard the movement of leachate due to their low permeability, and they also works as a final cap to limit the generated gases. The applications of soil liners includes: the soil liners are used to prevent the migration of contaminants from a landfill. They are used as a lining material to underground oil tanks to avoid oil contamination that may happen due to leakages from the steel tanks. They can be used as a lining for ponds to avoid a loss of water and to keep the water clean. They can also be used as a secondary containment barriers where they prevent leakages when the primary containment fails. The soil liners reduces seepage and can be used to construct cut-off walls around the waste containment facilities. Sources and types of ground contamination. The various sources of heavy metals include atmospheric deposition, sewage discharge, improper stacking of the industrial solid waste, mining activities, the use of pesticides and fertilizers, production of construction materials, chemical wastewater, nuclear waste, runoff, lead paints, petroleum spills, etc. The highly produced metal is copper, and highly segregated metal in soil is zinc than any other metal. Heavy metals disposed in the soil will remain in the ecosystem as they are not biodegradable by natural processes and extremely hazardous when they find their way into human bodies through the food chain. Now let us see the sources of a few metals. In that, first one is cadmium. This is a bluish white soft metal naturally reaches the atmosphere by volcanic eruption, ocean sprays and forest fires. The other sources are factories of polyvinyl chloride, alloys, solders, enamels, textiles, sewage sludge, phosphate fertilizers, steel plating and nickel cadmium batteries. Next metal is copper. It is a reddish brown metal naturally found in sandstones. The main sources of this metal are fertilizers, pesticides, building materials, municipal waste and industrial waste. The normal range of copper content in soil is 2 to 100 ppm and in plants it is 5 to 30 ppm. Next metal is lead. It is a bluish white or silver grey metal which is produced from the ore galena. The main sources of this metal include lead zinc smelters, glass, solder piping, ammunition, insecticides, toys, paints and batteries. Next metal is zinc. It is a white metal with a bluish tinge and its sources are factories of galvanized products, rubber, brass and bronze alloys, cosmetics, batteries, pharmaceuticals, metal coatings, paints and zinc based alloys. This metal normally ranges from 30 to 150 ppm in soils and 10 to 150 ppm in plants. So, soil contamination is mainly caused by man-made chemical alterations to the ground, which may be due to rupture of underground storage tank, application of pesticides, percolation of contaminated surface water, mining, oil and fuel dumping, leaching of waste from landfills or direct discharge of industrial waste to the soil. The soil contamination usually occurs due to the discharge of petroleum hydrocarbons, pesticides and other heavy metals to the soil media. Now let us see the impact of contamination on geo-environment. The indiscriminating disposal of heavy metals causes deleterious health effects not only by water contamination but also by entering the plant parts. The herbal products obtained from the medicinal plants grown in contaminated sites, if consumed, causes serious consequences on human health. Hence, the raw herbs need to be screened for heavy metals content before using them in medicines. Approximately 80% of Indian population uses Ayurvedic medicines which rely on herbal products. Since in 1978, more than 80 cases of lead poisoning associated with Ayurvedic medicine use have been reported worldwide, as there was no awareness that the traditional formulation contained heavy metals. The research on Ayurvedic products sold in the US showed high levels of lead, mercury, and arsenic, and this led to further investigation on quality and safety issues. Heavy metal contamination of vegetables cannot be underestimated, as these are the major source of food for many living beings, and intake of these contaminated vegetables may cause serious health problems. The toxins can enter the human body in many ways, such as the consumption of foods, beverages, skin exposure, and the inhaled air. The heavy metals accumulated in the human body may not only cause damage to heart, brain, kidneys, bone, liver, etc., but also displace the nutritional minerals from their original place. The heavy metal impacts on human health and their allowable limits as per IS code are presented in this table. Next topic is remediation of contaminated sites. The aim of soil remediation is to remove or reduce contaminant concentrations within soil to protect human health and the environment. The remediation techniques are broadly classified into three types: containment, to prevent the migration of contaminants, and second one is the removal, that is to transfer the contaminants to safe place, and third one is treatment, is to transform the contaminants to non-hazardous substance. The identification of suitable soil remediation technique depends on the soil and site characteristics, concentrations and types of contaminants, and the end use of the site after treatment. The different soil remediation techniques are discussed. In that first one is isolation or containment. This technique involves prevention of migration of contaminants from polluted site by providing impermeable barriers to prevent fluid flow. The materials such as bentonite, soil, cement, grouts, and geomembranes are used as caps to reduce infiltration, or walls to reduce groundwater contamination around the polluted site, to reduce the metal mobility by isolating it from the surrounding areas. The commonly used and economical barriers are slurry walls. This technique is suitable for isolation of contaminated soil or waste extended to deeper depths. Next one is the immobilization or solidification. The immobilization or solidification is a widely used method to remediate a broad range of contaminated media and waste, which prevents the migration of contaminants from the treated soil or waste. This technique has been used to treat radioactive waste and hazardous waste since 1950s to improve the soil for subsequent construction. Solidification binds the pollutants in a solid matrix by adding solidifying chemicals like liquid monomers, pozzolans, bitumen, fly ash, cement, and chemicals to the soil. The immobilization process includes development of chemical bonds to lessen the movement of pollutants by adding amendments to soil. This process is not appropriate for metals which do not form hydroxides such as arsenic, chromium, and mercury. This immobilization or solidification method can be executed as in situ or ex situ, and it is effective for treating large area with shallow depth. Vitrification is a solidification or stabilization process in which electrical energy is passed through electrodes placed in soil to vitrify contaminants. This method is effective for treating the contaminated soil of shallow depth and for low volatility metals such as arsenic, lead, and chromium. This reduces toxicity, mobility, and volume of waste, that is 20 to 40%, but it is an expensive method. Next soil remediation technique is size separation processes. The size separation processes are appropriate for highly polluted soils, and recovery of useful metals is possible with this method. They include mechanical separation and pyrometallurgical separation. The mechanical separation involves separation of bigger and cleaner materials from the smaller and unclean ones through several processes like hydrocyclones, fluidized bed separation, flotation, aeration, etc. Pyrometallurgical separation involves evaporation of metals from polluted soil by using high temperature furnaces. These methods are most suitable to recover mercury, gold, and platinum. Few metals such as lead, arsenic, cadmium, and chromium may require pre-treatment. Next method is electrokinetic processes. In this method, electric current of lower intensity is passed amid a cathode and an anode implanted in the polluted soil. The charged metal ions along with the pore water are subjected to migration and move towards electrodes. The treatment time and spacing of electrodes in the soil depend on the site conditions. This method is suitable for saturated fine-grained soils having a low groundwater flow where pump and treat techniques is not effective. The optimum moisture content of soil may be between 14 to 18%. Next method is biochemical processes. The important biochemical processes are bioleaching and phytoremediation. Bioleaching is the process in which the pollutants are removed or reduced from the soil using microorganisms such as Aspergillus niger, rhizopus, etc. Phytoremediation is the process in which particular plant species are used to absorb or extract the pollutants from the soil. The phytoremediation is effective for shallow depths of contamination and the treatment takes longer time. The next important method is soil flushing and soil washing. Soil flushing involves the removal of pollutants from the polluted site by water flushing. This flushing can be executed as in situ treatment only when the contaminants are water soluble and the permeability of soil is moderate. The in situ soil flushing is more suitable for soils with hydraulic conductivity greater than 1 into 10 to the power of minus 3 cm per second. Presence of man-made obstructions such as pipes and underground storage tanks may limit effectiveness of this technique. While performing the soil flushing at the site, there is a possibility of migration of pollutants into undesirable areas, and hence the site hydrology must be studied before flushing. Soil washing may be in situ or ex situ, which involves the mixing of chemicals to water to dissolve the metals, and its efficiency depends on the permeability of soil. The commonly used additives are diluted acids and other chelating agents such as ethylene diamine, tetraestic acid, ferric chloride, etc. Soil washing is cost effective only when the percentage fines in the soil are less than 20%. The commonly used flushing solutions are plain water, surfactants, and acids, bases, chelates, and solvents. Plain water can be used as a flushing solution for soils containing soluble pollutants with a distribution coefficient less than 10. The surfactants made of detergents or emulsifiers are effective at removal of hydrophobic contaminants and are suitable for low soluble organics. When the solubility is very low, co-solvents such as alcohol can be used to assist in enhancing solubility of hydrophobic contaminants. Acids, bases, chelates, and solvents are the solutions which are required to remove metals bonded to the soil by converting them to more soluble compounds. Example, chitosan, EDTA, sodium citrate, citric acid, tartaric acid, etc. The flushing solutions may be injected by either gravity or pressure. Gravity driven methods depend on infiltration due to natural hydraulic gradients, and pressure driven methods depend on pressure gradients or extraction pump. The leaching solutions are infiltrated into soil using different processes such as surface flooding, surface trenches, sprinklers, horizontal or vertical drains, etc. The other soil remediation techniques are incineration techniques and thermal desorption techniques. Incineration of waste can be performed by various equipment such as rotary kiln, infrared conveyor furnaces, liquid injection, plasma arc, fluidized bed, multiple hearth, etc. Incineration reduces volume and toxicity, but the costs are relatively higher. The advantage of thermal desorption over incineration technique is reduced amounts of gases produced, and hence it is an environmentally beneficial process. It requires less temperatures than combustion, and the treated soil can be reused. After treating the landfill waste, it can be diverted from landfills, which saves the space in landfills. Now let us see the factors influencing the selection of remediation technique. A number of critical technical factors need to be measured for selecting the effective and less expensive remedy. These factors are classified into three main categories: site characteristics, soil characteristics, and contaminant characteristics. That first one is site characteristics. The major factors to be considered while evaluating the site characteristics are site topography, site surface and subsurface structures or utilities, then site size, depth to groundwater and flow direction, etc. So in that first one is site topography. A detailed topographic map of the contaminated site has to be prepared prior to the selection of the remedy, including the areas of recent contamination by this site. All the existing and proposed above ground and underground utilities and structures which may constrain the cleanup methods should be located and identified on the site map. Some remedial technologies may require considerable space for staging and handling of materials and equipment. Hence, should be considered the site dimensions while selecting the remedy. The sites with shallow groundwater are not suitable for in situ remedies such as soil vapor extraction and bioventing, as they have a problem with upwelling of shallow groundwater and plugging soil pores. The characterization of both horizontal and vertical components of groundwater flow is necessary to locate the monitoring wells for monitoring the treatment performance. Next one is soil characteristics. The effectiveness of most remedial technologies is greatly affected by the type of soil, as it greatly varies with distance and depth. The critical hydraulic properties such as permeability and water holding capacity are greatly affected by soil properties and hence should be determined during the remedial investigation. The estimation of soil properties such as the permeability from grain size may sometimes lead to erroneous conclusions. The suggested properties to be determined are grain size, soil pH, soil moisture, soil temperature, soil permeability, etc. So the soil samples from the site should be tested for grain size and they should be classified. Total organic carbon. The high organic carbon content increases the adsorption and reduces the solubility and volatilization of these compounds. This can reduce the efficiency of remedies such as soil vapor extraction and soil washing. High organic content also adversely affects the bioremediation and chemical oxidation, as this organic content exerts an excessive oxygen demand. Soil pH greatly affects many treatment technologies. Extreme pH ranges are not appropriate for bioremediation methods, and a pH between 6 and 8 is normally required to sustain microbial growth. High soil moisture is undesirable for vacuum extraction systems and thermal treatment, whereas it is beneficial for bioremediation. The microbial activity, the rate of organic contaminant degradation and vapor extraction depends on the soil temperature. A temperature range of 10 to 45 degrees centigrade is suitable for microbial activity. Soil permeability greatly influences the efficiency of in situ treatment technologies. Low permeability reduces the capability of remedies like soil flushing, vapor extraction, and bioventing processes. Next one is contaminant characteristics. The contaminant characteristics to be considered for the choice of remedial technique or extent of contamination, contaminant concentration, depth of contaminant, and contaminant biodegradability. So at the site, the aerial extent of contamination should be determined to estimate the cost of remedial technologies. Average and maximum concentrations of contaminants at the treatment location should be determined to select suitable remedy. The depth of contamination greatly affects the cost of remediation, and the cost is much higher when the depth exceeds 20 feet. The rate of biodegradation is fast when adequate oxygen, moisture, and nutrients are present in the location, and are slow if optimum conditions are not present at the site.